welcome everyone. This is a new instance of the Flyte Community Sync, Flyte Community Presentations, where we give space to Flyte users to share what all the amazing stuff they're building with Flyte. I'm David Espejo. I'm part of the Union.ai team, and probably will find me more often in the Flyte Slack space, learning from you and trying to answer some questions. We try to do these presentations once per month. If you want to share anything you're building with Flyte, just let us know, drop us a message on Slack, and it should be not exactly a heavy lift. We try to keep it lightweight for you, but it's still a huge effort for you all to come here, and we are aware. So anytime it happens, we are really thankful for you doing this. As a reminder for anyone joining for the first time, Flyte is an open source project, part of the Linux AI and Data Foundation landscape. And Union.ai is the main contributor to the project and kind of the corporate sponsor behind it. We are mostly dedicated to maintaining Flyte and building the Union.ai platform based on Flyte. Anytime you want to ask questions, just do it in the chat. I will drop a note there so you can see it's a two-way communication channel, so you can drop your questions there and we'll do our best to answer them here live. If you're watching the recording and you have questions, feel free to join the Flyte Slack workspace and drop a question there. We'll do our best to give you answer. So today with us is Len. Len has been an amazing user, contributor, advocate for both Flyte and Union. He's kind of unstoppable right now. He's contributing a couple of plugins. He's been doing public speaking, mentioning Flyte. So yeah, really thankful for Len being here. And with that, over to you, Len. Welcome.
Thanks, David. Cool. I'll start by sharing my screen and give an introduction to myself and sort of review what we're going to be chatting about.
Awesome.
So the first thing, there we go. David, can you see my screen? Am I in presentation mode?
I can see your presentation mode. Mm-hmm.
Great. Cool. So my name is Len Sternad. Today I'm giving a Flyte community presentation on how to build scalable mosaic workflows with Flyte or Union with GDAL and Xarray. So just a little bit of background about who I am. I am a remote sensing machine learning engineer with about 7 years machine learning experience, about 4 years of remote sensing experience. Have a master's in statistics. Very eager to enable data scientists. I'm eager to advocate usage of PenGeoStack and Union.ai and Flyte, obviously, because I'm here today. And I'm also a builder of end-to-end remote sensing machine learning applications. Previously at Pachama, I was building end-to-end canopy height modeling all the way from ingesting data from raw source to making final roster predictions of canopy height characteristics for environmental modeling. And similar at Perennial, I was doing very similar things, building end-to-end soil carbon modeling. At Pachama, we had sort of our own self-deployed Flyte deployment, but I kind of fell in love with Union.ai at Perennial. We couldn't really afford a platform engineer to sort of manage things and ensure uptime and stuff, and we were able to hit the ground running. And so I kind of have been able to dabble in both the self-deployment and Union.ai deployed versions. I'm not currently between roles. I actually just started my new position last week at Whereabouts, and as a machine learning engineer, and I'll be focusing on building out all the roster pipelines for enabling a lot of our AI capabilities. And you can find me on GitHub here. Okay, so who are you and who am I sort of gearing this talk towards? You might be a data engineer looking for a new orchestration tool, and this might be relevant for you, this talk. You might be searching for an orchestration tool to build end-to-end ML applications, maybe sort of gearing towards more machine learning engineers to enable your data scientists, or maybe you're searching for a unified way to build experiments or data products. Like maybe you literally are a data scientist and you are eager to learn how to use a workflow orchestration tool to sort of combine all of your steps to make your experiment sort of run end to end and reproducible and all that. Or maybe you're currently using GDAL and want to see GDAL in action with Xarray, Flyte, or Union and Dask. So agenda today in the talk is going to be, first, let's just introduce a notion of standards for machine learning and remote sensing geared towards data models, compute, and mosaics for end-to-end applications. These are the sort of standards that I've found a lot of data scientists appreciate. It allows them to wrap their head around what is the input and output data type and how is it familiar, sort of in the sense that NumPy and Pandas is familiar. Xarray sort of gives us that same exact thing. So how can we support those data types between tasks and workflow orchestrator? And how can they have access to those intermediate tasks to inspect intermediate results? Then we'll introduce Flyte and Union.ai. Probably won't spend as much time on that because most people here are probably aware of what Flyte has to offer, what Union.ai has to offer. And we'll review GDAL's GTI driver. This is somewhat in the weeds, but if you are doing remote sensing, and I know that there are a lot of Flyte and Union users that likely do use GDAL and likely do build large-scale mosaics, this will be of interest to you. And then finally, we'll review an example of an end-to-end mosaic workflow and some of the caveats. Cool. So yeah, first thing, just sort of talking about the standards in remote sensing and machine learning that I try to bring to some of the teams that I join. I did this at Pachama and did it at Perennial, and sort of the thing that really worked best was sort of standardizing some of these data models. There are some caveats, but Xarray sort of gives us this view. It's a great candidate to model mosaic data sets. Think of it as like one large image. We can see the dimensions here. There might be a time axis, there might be a band axis, there might be a y and an x-axis where each of these y and x's may index coordinates themselves. That could be latitude and longitude. Bands could be a string, such as RGB, red, green, blue, near infrared bands, things like that. And then time might be an actual date time coordinate. So what we get here is a really nice model that gives us a model of a large scale array that could sort of be arbitrarily large, that can be arbitrarily chunked, and those chunks can correspond to different file formats. The talk today focuses primarily on Zarr as the backend. And the plugin that I'm actively working on in FlyteKit right now is to persist Xarray datasets to Zarr between tasks, sort of on your behalf, so that you don't have to pass around a string for inputs and outputs, and explicitly open and explicitly write to Zarr. So this is a nice view of what the Xarray dataset looks like, what the cube looks like, this multi-dimensional array. And I think that this is a super powerful data model, especially to bring to Flyte and Union.ai, because it sort of is a one step closer to enabling production-ready scientific compute. A lot of scientific endeavors sort of use this model. Xarray is kind of ubiquitous in the scientific community. And this, in addition to other compute tools like Dask or Ray, allow people to build very large scale multi-dimensional arrays. I mentioned before that there could be a caveat, and you might not just simply be passing one of these things. You might have many of these things, in which case it still applies. We could still use MapTask. We can use MapTask, for example, and sort of build out multiple Xarray data sets and manage a list of these things. But just to keep the talk simple today, let's just think about a use case that might need one very large Xarray data set. This one, obviously, not very large. We got 24 gigabytes, where each chunk's about 16 megabytes. But think about the case where this might be terabytes or even petabytes. So this is sort of a standard that I think has been really useful for teams. You can easily slice out bits of this Xarray data set and only read the relevant chunk that you're touching. It allows people to inspect really large scale things because we can open it in a lazy way and inspect subsets of the data very easily. And if they want to inspect the whole thing, then, well, they'll need some access to some distributed compute. Okay, now what about compute, the compute side of these standards? Dask has actually worked really well for operations on Dask array-based Xarray datasets, but it has some limitations. It's really great for a reasonable number of tasks that are short-lived, for example, like interpolating over the time axis of a reasonably sized and chunked Xarray dataset. So there are some caveats there. If chunks are too small, the number of tasks explode, and submitting that entire task to Dask, that task graph to Dask can sometimes blow up. So in this talk, there's an opportunity for a whole hierarchy of different levels of parallelism. And I'll try to sort of highlight where my mind tends to sit and which levels of parallelism I try to focus on. Also, compute standards around workflow orchestration have been huge. So many teams that I have joined essentially get a data product out by running a notebook that may or may not be connecting to some distributed compute like a Dask cluster externally, but they still have to like babysit this notebook, right? You have to go from cell to cell to cell, make sure that it computes in order, right? There's no versioning and all of these things. And that's really where workflow orchestration can just help give them one single entry point where we have end-to-end type processes with individual tasks that can possibly be cached with intelligent retry, and it's very easy to update code and make code changes and register your code changes, and all the things that Flyte gives you, Union gives you, for example. One thing that I'd like to mention is that, and that I think this sort of helps differentiate where we can have levels of parallelism, is that Dask is not a workflow orchestration tool. Even though it can enable you to work on a really large scale Xarray dataset or any type of, or a data frame, for example, you still, again, if you're in a notebook connected to a Dask cluster, you still have to manage from one cell to the next. And that means that your computer needs to be on and you can't close it and go for a run unless you're running a Jupyter server and the processes remain intact. So these are just speaking, this slide is just speaking to the standards in compute that I've tried to bring to a lot of data science teams to sort of enable them to think bigger and feel like they have like basically infinite compute at their fingertips. All right, so the last point I'll talk about with standards in remote sensing machine learning are mosaics with GDAL. So we're sort of diving in a little bit to very specific use case of building something like this data set here, but at very large scale. So the assumption here is that you have a list of analysis ready, like temporally stackable TIFFs for an AOI, with so many that using GDAL from the command line might not work in a reasonable amount of time. Okay, so let me just back up. For those that are not familiar with GDAL, there's a ton of functionality. It's all written in C++. A lot of people with a GIS or remote sensing or Earth observation background, most of them are going to be using GDAL and likely from the command line. And let's just take a second to just define what we mean by mosaic. So a mosaic is essentially stitching together multiple scenes into one large image. So if we go back to our example here, and we think of these two dimensions, X and Y, as one single image, when you go to access TIFFs or GeoTIFFs or any of these other file formats that represent raster data sets, you may only have a portion of the complete area of interest. Meaning, if you go to NASA and you're like, hey, I would like this one specific data set, they're going to give you a catalog of files that might only be a very small portion. And so in order to make this full data set, you're going to have to get all of the tiles that are going to cover this area of interest. Okay, now that you have a list of these raster data sets that cover the area of interest, we need some way to stitch them together. They might be in different coordinate reference systems. They might need to be reprojected because they might not land, these pixels in the source images might not land on the pixels in the target grid. So we might have to do some massaging. And these are the types of things that are all done for you by GDAL. And you can do this from command line. You can say, here's my list of TIFFs, or here's my list of raster datasets. Go build me one raster dataset. But that's on command line. If it's on the command line, it's running on your computer, or maybe it's a VM, but still you can't arbitrarily scale out unless you use a more delayed fashion to represent the final output of your mosaic. So think about the case where you have 100,000 of these raster data sets, and they might all be in different coordinate reference systems. So they might have to be, and they might be at different resolutions, meaning the pixels themselves will have different geospatial encodings and might need to be potentially reprojected and resampled to that specified grid. Well, there are two common solutions with GDAL, and I originally gave this talk at a Pangeo showcase to sort of highlight the two approaches here that can be rather common. The first one is called VRT. So that's a virtual raster transform. So if you have a list of tiles that are all in the same coordinate reference system, you can construct a VRT. This VRT is essentially a mapping such that when you open it in something like OpenRaster.io, either using Raster.io or Rio Xarray, you're providing the compute the instructions of like how to build the final target, how to build the final grid, and how to do the resampling only, because we're in VRT, to land it on that final grid and insert those values. However, if you have multiple sets of tiles and they're potentially in different coordinate reference systems, which is actually very common in the Sentinel-2 and Sentinel-1 catalogs, for example, the world is sort of covered in multiple coordinate reference systems. You might have an area of interest that overlaps two UTM zones, which are two unique coordinate reference systems, and they do that to reduce geospatial errors incurred by basically trying to get the globe, which is spherical, to land on a grid, right? Because we're ultimately trying to get this into a multi-dimensional array, which means a grid system, and the grid doesn't perfectly map to the sphere, as we can all imagine. So some of the downsides of VRT and warp VRT, and I know I'm sort of diving a little bit deep into sort of very specific remote sensing bits for a talk in the Flyte community presentation, but it's worth noting that at least mentioning that VRT has to make one HTTP request per file. So if you have 100,000 files or 1 million files, it's going to take quite a long time for GDAL to wrangle all the metadata that it needs to build this final mapping. Warped VRT can then reproject those things. So you have to do this nested chain if you do have sets of tiles in different coordinate systems, and it can start to add up. You need configurations in GDAL to make these requests in an efficient manner, and it's a lot of thinking. It's a lot of configuration in order to get this to function well. But recently, GDAL put out in 3.9 their tile index, GTI tile index, and essentially all that this is think of it as a Parquet file or a flat GeoBuff, a vector data set that actually index the rasters themselves with some metadata like the actual geometry that corresponds to that box, all that metadata that GDAL goes and gets in those HTTP requests. So you're saving all of those requests by just providing that data up front, and you can get this immediately from a stack catalog, for example, which is sort of the new standard for cataloging raster data sets. So this is this file itself is very quick to construct. This one is not, and this whole operation in Xarray, in Python, using Rio Xarray is also delayed. So you can build this very quickly, and then you can open it very quickly. It's all computed in a lazy fashion. The only thing that's computed are the coordinates that define that grid. So you could take it one step further and think about, okay, well, at some point, if the resolution is cranked all the way down and your area of extent is as large as possible, that the coordinates themselves might be really large, but there's a lot of active community development around delayed coordinates themselves, functional coordinates. And I think that's going to be the thing that really enables like arbitrarily large scale mosaics. So I know it's kind of a deep dive in some remote sensing nuances, but what this is going to do is sort of like set the foundation for how to build something like this that's actually large scale in Flyte and Union.ai. Cool. So a quick summary, remote sensing and machine learning standards. Okay, team, let's unify workflows to operate on Xarray-based mosaics when possible. Try to assume whenever possible, we'll have Xarray in and Xarray out. This way we can just focus on the task and isolate things. Become familiar with Xarray. It's going to be your new favorite library to use, akin to something like pandas and NumPy. And let's use GDAL to standardize on mosaicing operations, leaning towards GTI when possible. And finally, let's pick a workflow orchestration engine that enables end-to-end applications, easy, quick experimentation, use of Dask through a Dask plugin, and also fast iteration, intelligent retries, caching, versioning, infrastructure as code, all of these things. Cool. So this is the page I'm probably not going to spend much time on. If you're here, you probably know what Flyte is, and that there's great documentation and there's great deployment guide, and you're likely on the Slack channel already, and there's really great engagement there. But I would like to at least make a slight plug for Union.ai. When I joined the team at Perennial, we were able to just really hit the ground running by letting Union.ai manage the deployment for us. And it really was, we were able to work at incredible speeds and get things up and going. We never had to worry about uptime or anything like this. Like, in addition to just general deployment management, there's so many other bells and whistles that really make the experience of Flyte super, super nice. And we'll get a quick view into what the UI looks like in a second. Also want to mention like feature requests. The speed at which they respond to feature requests is incredible. And the Slack channel engagement in our own private organization is just amazing. It felt like I was working with, it felt like I had new coworkers and that really cared, and it was great to just have conversation with them and work with them. Cool. So now we'll jump into a quick Flyte Union demo. I do have a repository called Flyte Mosaic that sort of demonstrates this whole end-to-end building mosaic that's arbitrarily large scale. But what I want to do is sort of just demonstrate what this plugin allows us to do. So first, there are two plugins that I'm going to be taking advantage of in this very simple workflow. So we probably have all seen workflows before. In this case, I'm going to be building an Xarray dataset. I'm going to transform an Xarray dataset, and I'm going to compute the mean. So two things. Let's go look at what this actual task decorator looks like. We all have probably seen this task decorator. I've enabled cache. I specify cache version. I'm enabling the deck for so that we can render those nice Xarray HTML summaries that we see here, something like this. And I'm also using the Dask plugin. So all the heavy lifting of this work actually is all embedded in the Dask plugin, and it could probably be swapped out for Array plugin as well, as there is support for Dask and Array, but I have yet to investigate that and give that a shot. It probably would be a little bit more robust and be a little bit more production ready. So I would urge people to consider doing Dask and Array if trying to push this to their absolute limits. So yeah, shout out to Bernard Stadelbar, who is has been a core contributor to Flyte and was the one that actually contributed the Dask plugin. This plugin that I've added to support Xarray datasets just leverages that behind the scenes. So I have actually not made any contributions to this plugin, but wanted to mention that these two plugins are going to be working in tandem. It's currently not. So one thing to mention is that the Xarray plugin is currently not yet released on FlyteKit, and I am installing it just directly from Git here, from my Add Xarray plugin branch from the plugins community. FYI. So cool. So now that we know we have specified a task that uses a Dask cluster with 28 workers, each with 2 CPUs and 7 GB of memory, we can sort of demo what this actually looks like. Okay, so first things first, let's go build an Xarray data array. And we're going to use Dask to specify chunks so that when we actually do this random, when we build this random array of this shape that will roughly amount to about 200 gigabytes, that each of that array itself is chunked into these sizes, so that'll amount to some number of megabytes, probably 16 or 128, we'll see in a second. You can specify the dimensions that correspond to this Xarray and the coordinates. So you can see that you can see kind of roughly like what it looks like to build something that would be akin to this sort of schema in Xarray. We're not diving into the guts, and we probably won't have time to dive into the guts of like what it would look like to build something like this with GDAL's GTI, but feel free to go take a look at Flyte Mosaic to check to see how I'm actually doing that. So think about this being returned from a function that says go build an Xarray dataset from GTI. And so what I want to demonstrate here is how this can be automatically persisted using the plugin that I added. Next, we have a transform Xarray dataset. And what this does is sort of demonstrates like how ergonomic Xarray datasets are. So because I have the Dask plugin, this is going to be opened from Zarr. Everything's going to be lazy. No compute is happening here. I haven't called compute or anything like that. But then when we return the Xarray dataset, the plugin itself will know to write this out to Zarr. So between these tasks, we're reading and writing to Zarr in a lazy way that's taking advantage of the Dask cluster to speed up this computation. So when you call to Zarr, that's actually triggering all the compute that's happening behind the scenes when you're calling these operations. Okay, why sort of abstract that away from some users? Okay, it's not going to work in the general case, but what this allows people to do, like such as your data scientists or people who don't want to think about distributed compute as much, is to just express the operation that they want in Xarray code and have the Dask cluster and persistence to Zarr be handled for them automatically. It just greatly simplifies what this task looks like. The alternative would be passing a string to the store saying Xarray open Zarr, writing this style function, and then calling to Zarr, and then returning the string, right? So we've gone from like 4 lines of code to 1 line of code, just allowing the user to just solely focus on, expressing themselves in terms of Xarray code. Cool. And then the final task would be computing the mean, for example. And again, this is just like a Dask workflow example. That's sort of an example of like an end-to-end Dask workflow that builds Xarray datasets, transforms them, and computes the mean. This might actually be, hey, load my Tensorflow model, load my PyTorch model, apply it to that Xarray dataset in batches over the area of interest, and then go write out the roster of all those predictions, for example. This is just a simplified view. Cool. So now we could go take a look at what this looks like. So the Dask workflow example, what we see here is that it is a Dask task and that the Dask dashboard is available. I'm not here to demo the Dask plugin, but while this is actively running, you can click this Dask dashboard link and you can actually go see Dask plugging away and computing all the bits in a distributed way on the Dask cluster. When this task actually launches, it says, hey, Dask operator, go spin me up a Dask cluster just for me. And that's exactly what it does, very similar to what Xarray does in the Xarray plugin. Because I have added some mild support for HTML, you can see if you enable the deck that you can get a nice view just to give a sanity check of like how big is it, what's it chunked like, how big are the chunks, how big is the final data store. And then same exact thing with this transform Xarray function. We can look at the deck and see that, okay, now it does have an input. It's still 200 gigabytes because all we did was some band math. We didn't do any reductions along any of the dimensions. And we can see that here's a nice sanity check. The shape is the same, right? As we would have expected. We're not doing any shape change manipulation like aggregation, like I mentioned, but we can now see that the same bands are there, the same coordinates are there. The only thing that's different is that there is, we go from 2 graph layers to 3 graph layers. And this is just a very Dask specific thing. So that is just a quick overview of the Xarray plugin and sort of assuming that people already have a demo of, or already has a familiarity to Flyte and Union. I'd like to roll back a second and just mention like how beautiful the Union AI version of the UI is. It's just really nice. There are a lot of features that I'm not going to get into, and it's worth checking out the docs. Everything from cost to figuring out who ran which workflow to workflow builder, artifacts, all of these things that are really nice apps. A lot of things, just a plug for you all to go check it out on your own if you currently have a self-managed Flyte deployment and are considering Union AI. Cool. Moving on. So back to GDAL drivers and mosaics. Kind of want to just talk about the pros. The real Xarray open roster IO, with VRT is actually delayed. So what this allows us to do is take advantage of that same plugin, the same Dask plugin, and the persistence plugin that I have to write to and from Zarr, and allows it to be relatively straightforward to build GDAL VRTs or warped VRTs and use them in a delayed fashion. The cons to the VRT approach, as mentioned before, is that we have to make a request to each file to get metadata and yada yada. So I've already sort of covered some of these slides, and I'll jump back in presentation mode. In GTI, another thing that I mentioned is that it actually does support heterogeneous CRS. So it's going to do the reprojection and resampling on the fly for you, and it should easily integrate with Stack Parquet. So if you have a stack catalog, you can just dump it out to Stack Parquet, give it a GTI extension, and you should be able to load it directly into Rio Xarray, for example. And if you already have the metadata associated, no requests are needed, and it can be opened directly and in a lazy fashion to sort of stay in the realm of like lazy Xarray and Dask. The downsides is that you need a slightly newer version of GDAL, which people are probably already onto anyways. And then there are some other caveats around a lot of the GDAL configurations that also the VRT approach you have to keep in mind also for the VRT approach. Cool. So I'll probably I was sort of targeting 30 minutes and I'm already 3 minutes over. So maybe I'll spend 5 more minutes just sort of reviewing what my Flyte mosaic repository is doing, how I am achieving building really large data sets that are even too big for the Dask cluster, which might not be a good fit for the Xarray plugin that I've added to automatically persist things to Zarr. But these are sort of some of the patterns that I've discovered. And I wanted to give some insight into how I've been able to bypass issues with the Dask graph being too large and things of that nature. Cool. So I'll jump over to code very quickly. So what I'm doing, the main entry point here is that we want to build a dataset mosaic workflow. So we have these very common inputs like bounding box. What's my region of interest? This is a bounding box of the latitude, longitude points on Earth of my area of interest. Which times do I want to build the data set for? Like what is the temporal dimension going to look like? Which data sets am I going to add? Where I use enums to sort of map to protocols that specify where to access scenes from particular data catalogs. Maybe it's NASA, maybe it's some university server, which is the case I implemented for, specifying the resolution of the final grid, the CRS of the final grid. This is like the coordinate reference system. So if you're familiar with Earth observation, GIS, remote sensing, you'll know what this is. Chunk partition size, this is sort of a hyperparameter to dictate how large each task should be when I go and actually build that particular slice of the data set concurrently with map task in order to enable the maximum amount of memory that's going to be used by that particular task. And then the final target XY chunk size. This is going to correspond to the chunk size here. So you can see 1, 1, 2048, 2048. In this case, it would be 1, 4096, 4096, which will have implications on the size of the chunk. So so there are some two higher level inputs that sort of parameterize the structure of the final Zarr store that represents the Xarray datasets that will have some downstream implications on tasks that you'll have in the future. So maybe if you're operating on this mosaic, you might want larger chunks to have fewer tasks because your process can actually handle larger chunks. Or maybe your process can't, and then you would want to rebuild it in using a smaller chunk size. Or you can add a new workflow to re-chunk that Xarray dataset so that you have reformatted it in a way with a chunking scheme that's going to be more conducive for your downstream operations. So everything below here is sort of like operation-specific hyperparameters that might dictate the success of the final workflow. So one thing to note here is that it's really nice actually to call workflows within a workflow. It helps me separate and isolate concerns and implement these things in parallel. One team member can go work on the ingest workflow. One team member can go work on the build scene features workflow. I can assume the output types from these that have this very specific format, and I can hit the ground running. So one nice thing about workflows in general and sort of stamping them out, sometimes I'll start with a workflow definition, and then we can parallelize work, and we define the interface for these specific workflows. And it's up to the user to implement those details, abiding to the contract that we sort of agreed on. And again, that has made it really nice to be able to like parallelize work on teams. So just wanted to mention that bit, some things that I've learned. Cool, what else is worth mentioning here? So the ingest scenes workflow at a very high level is going to go reach out to whatever data set you have provided to its tile source. It's going to pull down all of the scenes that are needed for that area of interest. This might be red, green, blue bands from Sentinel. This might be VV and VH or HV bands from some SAR data set. And at this point, we'll have a GeoPandas data frame. Okay, another quick plug. We see that in this workflow, we're actually returning a GeoPandas data frame, and it's not being serialized because I've added another plugin to actually support GeoPandas data frames that automatically persists to Parquet. So you know how in Flyte, if we return a pandas data frame or any other data frame, it will automatically get persisted to Zarr for us. Same exact thing with this plugin. It's relatively straightforward. All we're doing is persisting it out to Parquet. But what this does sort of give people who work with GeoPandas data sets a nice mechanism to it gives Flyte users who are Earth observation, remote sensing, GIS focused, a nice step towards working with very common data structures that we use on a day-to-day basis. Cool. So both of these, so that the GeoPandas data frame that's returned is an index. It's a vector data set with a bounding box geometry column and a URL column pointing to where that particular raster data set is on blob storage. So think of this as that GeoParquet or potentially that GTI index that we've been chatting about. Scene features is going to actually distill those scenes into feature-ready cogs or feature-ready cogs. So we ingest them in a way that's going to have a specific block size that's going to be in the cog format, so that headers are at the beginning, metadata is in the header of the file, so we have much more efficient access to the underlying tiles if they're needed. This is sort of the step that we take to optimize the file format and put it in a very nice concrete standard in format using cog in our own bucket in the same region of the compute that we're running things, so we don't incur egress costs and all these things. Okie dokie. So GTI has one more caveat. Okay, it's 10:40. I'm going to take 5 more minutes and wrap things up. GTI doesn't have a temporal dimension, so we have to build one GTI per data set. And so now that we have multiple GTIs, we can go sort of build those in parallel using map task, and this is going to be per data set, per data set that has its own unique consistent set of bands, and per time. So per data set and per time will be the number of GTIs that we have here, and then we'll go build a target mosaic task. What this task does is basically goes and builds the Xarray data set. So this is all going to look like code that we might be familiar with, like Xarray concat over the time dimension, and then we're going to concatenate across all the data sets along the band dimension, and the build GTI Xarray data function is going to just be this Rio Xarray open raster IO, here's my GTI. So sort of the things that we've been alluding to with some specific open quarks and chunk size being passed to it. So backing up here, we now have a lazy view into our data set that might have this type of schema. And when we call to Zarr compute equals false, we're not actually computing the data in these in the array. What we're doing is we're computing the coordinates, writing out the entire sort of Zarr structure without actually calling compute on the underlying data that's going to be put in there. What this allows us to do, and we'll begin to wrap up the talk here, is to write partitions of chunks. So an integer multiple of chunks at a time that will meet our criteria of chunks partition size. So in this case, I might actually build partitions to slice that lazy data set, chunks that are going to be at most that chunk partition size. This sort of puts a constraint on the maximum amount of memory that's going to be needed that might be tightly coupled to the requests and resources for that specific task. So what we see here is the same build GTI Xarray code, right? We have opened it in a lazy fashion, but now we have this GTI partition data class that has that gives us the ability to index into which region we want to slice out of our data set. So we say, hey, lazy data set, give me that one region that corresponds to this partition, and let's only compute that, which is implicitly computed when we actually call to Zarr with compute equals true, which is the default. And we're going to write it to that specific region. And we're going to do this concurrently using map task, because Zarr supports concurrent writes, but only at that across all the chunks. You can't write to the same chunk at the same time, and that's why we're doing integer multiple of chunks, so that we don't accidentally try to write to the same chunk. And this has been a really nice pattern for me in the past to kind of get beyond the Dask cluster. It obviously has the limitations that map task does. We might not want to go above and beyond 10,000 tasks, for example, or 5,000 tasks, for example. But with that limitation and keeping in mind the chunk size partitions and increasing the resources for that task, that gives us the span of quite large data sets that very easily can reach in the hundreds of terabytes sized data stores for Zarr stores for that final Xarray data set. So yeah, this is sort of what I have in Flyte Mosaic, and I whipped this together in about a week between jobs. And so it's not perfect, but what I wanted to do is just put something out in the public, what's worked for me in the past about building this target data set in a lazy fashion, and then using map task to write to those partitions in some parameterized way that allows us to scale sort of arbitrarily with caveats. Cool. So I'm gonna take one more minute here just to sort of wrap things up and talk about some caveats, and then that will be the end of the talk. So there are, so we've already mentioned map task prefer, you don't want to submit more than 10,000 tasks, because each task in Flyte corresponds to a pod being spun up on Kubernetes. So there are some things that you want to consider there. When using the Dask plugin, code needs to be in the container. Fast registration is great. In Flyte, it's been truly amazing for insane iteration speed, but it doesn't work with Dask. And there are ways to inject code into the Dask cluster, but you might have to push to CI or rebuild your container locally if, for example, you are importing code from a module that's not inside the current module that, Dask will be pickling that code and sending it to the Dask cluster. There are some caveats there. We partition chunks in integer multiples to submit work, like I've mentioned. The GTI driver is sticky, so don't call compute on the full target data set. It's literally just there to sort of stamp out what our final grid is going to look like. GTI has recommended specific metadata. Go check out the docs and make sure that if you are using GTI to build large-scale mosaics, that you're doing it in a way that gives GDAL a pass on needing to make requests to each of the underlying files if you provide that metadata. And then GDAL config matters a lot. So it's worth mentioning, it's worth quickly jumping to some of the configs that I think have worked well, and I've actually parameterized them by some of the expected memory usage. So it might be worth checking this out. I've got a lot of defaults for debugging and debugging the actual requests that are happening behind the scenes. I would love to get people's feedback on what's worked for them. This is often a topic of conversation with GDAL. And yeah, another thing is blob contention can occur if GDAL isn't building efficient cache. So what I often do is sort of another kind of caveat here. Very quickly is that Dask, I use the single, so when within that partition that might have multiple chunks, I actually set the Dask scheduler to be single threaded, because behind the scenes, that's going to submit in serial one chunk at a time to GDAL, which is using multiple threads to build that final thing when we call compute to Zarr. So what this allows us to do is build a meaningful cache as we go from one chunk to the next that likely overlaps cogs. And so if that cog is already cached for that one chunk, that chunk next to it is very likely to already take advantage of that cache that GDAL builds. So that's why I use single threaded. It builds these chunks in serial in order to build a more meaningful cache. And we really get the speed up from GDAL, enabling GDAL to use all of its threads rather than using Dask. Dask is just a way to manage submitting chunks at a time, which I mentioned here. And yeah, there are so many ways to parallelize things, right? Like we could do, like this could have been multi-threaded, right? And then that's going to be inside of a task that's being run inside of map task, or who knows, maybe this task itself has a Dask cluster, right? And then in which case we're taking much larger partition size. And then for map task, we have multiple concurrent tasks that are running, each of them kicking off a Dask cluster, which obviously is could be a lot of overhead for Flyte and Union, but yeah, there's so many options, right? There's just levels on levels on levels of just, yeah, it's just inception of parallelization. So a lot of things to think about. Okay, so that sort of concludes my talk. I know we don't have much time left. I know I kind of went over my expected time, but yeah, thanks for being here and listening to some of my very nuanced caveats of how to build large-scale Xarray data sets in Union and Flyte.
That was awesome. Thank you, Len. And yeah, thank you for taking the time to go over the no short amount of caveats that are present in the data processing in the Earth observation context. So yeah, thank you so much for also building solutions that will actually help a lot of folks out there. Yeah, I don't see any questions so far in chat. Yeah, the idea is that we will work on a blog post out of this, kind of keep it going, and we are ready to capture any question you may have after this session. But yeah, if no question whatsoever, I think we're good to go.
Cool.
Yeah, thank you again, Lane, for coming and sharing with us. Thank you.
No problem. Thanks for the support, David. I appreciate it.
Right. See you, everyone. Thank you.